Hello and welcome to my convolutional neural network in its simplest imaginable form in PyQt Python. This GUI is to a large extent built in a GUI that I used in a previous video, so you might want to check that out first. You can see the link. So this is the simplest possible conv architecture I could think of. And before I start going through it, for your information, I'm purposely avoiding certain design choices and concepts from the beginning, so be aware of that. It's going to come later. So what's different from the normal ANN that I did in the previous video? Well, first, I'm using fewer hidden neurons here. There's only 2 instead of 3 or 4 in the last video. And also there's 3 inputs instead of 2, and they are also connected with these black lines that I drew. And that's a requirement for a convolutional neural network to work well, is that there is some local connectedness in the data, so that this input has more in common with this input rather than this input. I also changed the synapses so there are no predefined connections here, but rather the connections are made on the fly when we see a certain part of the image. So either they can be connected this way when we put a filter over this part of the image, and then this neuron is activated. We can see that these connections are made. Or the other case is this: when the filter is here, then the connections are made this way, so that this neuron is activated. And we can think of these 2 red dots as our eyes. This eye is looking to the bottom side of the filter, and this eye is looking to the top side of the filter. So that's how the connections are made. And the biases are connected to everything just as before. One pretty scary thing to note here is that we have many inputs and not so many neurons to handle the inputs. So the complexity of our brain here, our model, is smaller than the real world out there. It's like an analogy for how we humans and other organisms deal with our situations. So we're stuck with our 2 neurons, and we somehow decided that each of these 2 neurons is capable of analyzing 2 inputs that are next to each other at a time. So then we get this filter, and we can then slide this filter or convolve it over our whole input in a stepwise fashion to make the propagation of signals as simple for our brain to deal with as possible. A couple of key CNN concepts, which takes a while to wrap your head around and are worth repeating, is that this neuron doesn't in any way represent this eye. Actually, it's not like an eye, it's more like a connector or a neurotransmitter or something. This neuron cares about the information retrieved when the filter is lying on this location. So it's a bit confusing here because we have only 2 filter locations in this case, but we also have a filter size of 2. But this neuron doesn't care about the filter size, it only cares about the filter location. And another weird thing to note is that we have only 2 signals at any time here, but there are 2 pairs of synapses back here, and that the weights between them are shared. So we can see that these values don't change when we switch the filter location. So if I'd been less lazy, I would have actually drawn out the thickness of these lines to represent this number. So we can think of this line and this line as having thickness 10, and this line having thickness 7. And there's also 1 bias for each filter location. Before I'm going to dive into the forward prop and back prop procedures, let's take a look at the data I'm going to work with. So I changed the number of inputs from 2 in the previous case when we solved the XOR gate using a normal ANN to 3, because I think 3 is the minimum inputs needed to build a dataset for which it would make sense to use a ConvNet. And this is usually not what you see in deep learning tutorials. They usually throw something way more complicated at you. So we have 3 inputs, and we want the network to output a 1 when we have 2 ones next to each other. This looks really simple, but we can think of this as representing something more complicated. Let's imagine that this dataset represents images, and this is the left, this is the middle, and this is the right of the image. And we're looking for cats in these images. And whenever we have a 1, we have a cat feature. And a cat is 2 cat features next to each other. So here we have a cat, and here we don't have enough cat, and here we have enough cat features, but they're not connected, so it's like cat with hole, so it's not a cat. And here we have too much cat. It's like a deep dream cat monster with cat everywhere, and it should not be a cat. But this actually represents a pretty interesting case and problem for deep learning, because it's hard to build an algorithm which actually spits out a 0 here. And some humans would classify this as a cat, but I would say that this is more like a what the heck is this cat monster kind of thing instead. Even if we take away this data row, our ConvNet in its current form is not going to be capable of solving this problem. And I was considering changing the ConvNet architecture to make it capable of doing it, but I think it's really meaningful to walk through why it doesn't work in this case. But let's first go through a whole forward prop and back prop cycle. And I'm not going to do that for this date row because it's kind of boring, nothing happening. So I'm going to do it for this row. And I'm also going to set all weights equal to 1 to make it easier to follow. So we'll load this data row, 0, 0, 1. And then we place the filter over the top here. And we're going to forward propagate to this new row now by taking this one times this one, plus this one times this one, plus this one times this one. So it's a dot product as the input here. And then we run this input through the activation function, which is the sigmoid, to get the output from this neuron. And then we do the exact same thing for the other filter location here to get the output here. And now we're done with this convolutional layer, and then we can proceed to our dense layer, which is over here. And here the forward propagation works just the same as in the normal ANN. So we get our dot product here, and we run it through the activation function to get the output. And now we're going to calculate the error here. So we take the expected value minus the output to get the delta. And then we square this delta to get the MSE, the mean squared error. And then we take the delta and multiply with the derivative of this output to get the delta gradient. So we're like moving to the other side of this neuron here. In the previous video, I had the delta gradient placed here, but since we are on the left side here, it's better here. So now we're going to backpropagate, and over here in our dense layer, the backpropagation works just as in a normal ANN. So when we're going to calculate the delta weight of this synapse, we're going to take the delta gradient and multiply it with the output here. So we can see here that delta weight of this synapse is bigger than for this one because the output is bigger here. And for the bias synapse, the delta weight is the same as the delta gradient here because the output here is always 1. So now we're going to backpropagate to the convolutional layer over here. And it's going to be in a stepwise fashion because we have 2 filter locations. So we begin by placing the filter over the first location. And now we're going to backpropagate to calculate the delta weights over these 2 synapses with regard to this neuron, because this neuron has been responsible for the propagation of signals with regard to this filter location. So for both of these synapse weights, we're going to begin by taking the delta gradient, multiply with the weight over here, times that with the activation function derivative of this output, and then multiply it with the corresponding output here. So since both of these outputs are 0, both of these delta weights are going to be 0. But we're not done here. We're going to store the delta weight values for these 2 synapses now, and then place the filter over the next location and calculate the delta weights with regard to this filter location and this neuron. So we're going to take the delta gradient, go down this path now, and get some new delta weight values. And we're going to add these 2 delta weight values to the old ones we stored from the previous filter location. And unfortunately, both of the outputs were 0 here, so we're actually not storing anything other than 0, so it's kind of boring. But we can see here that the delta weight for this synapse is still 0 because both the connections here were always ended up being 0 because the outputs were 0. So the bias delta weights, here it's going to be exactly the same as this delta weight because all the values here are the same, and these values are calculated the exact same way as for these ones. It's just that there's always a 1 here. And this value is actually bigger than this one unsigned. And you might wonder why that is, because this neuron here has a bigger input and a bigger output than this neuron. So why is the network saying to a neuron with a bigger output that it should be punished less for the error than a neuron with a smaller input and output? And we're using the sigmoid function here. So the sigmoid function derivative peaks at 0.5 and then it levels off when it goes towards 1. And I don't really get the intuition for that. I think it might have something to do with that. We assume that neurons with a weak input are not expected to have like stabilized or converged on something, so they need to learn more and therefore they should be punished more. But if we would have used the ReLU function, which is normally used for CNNs, then both the derivatives here would have been 1. So then these values would have been the same. Now when we're done with one of these cycles, we're going to update the weights just as in a normal ANN, either with pattern learning or a batch learning. And I'm going to do pattern learning now so we can see the weights updating immediately now. And then we load the next data row, and it's going to be 110, and I'm taking them from this mock data set that I'm just using to show you how this works. So we run through the whole cycle again. And now we can see that the output is smaller than the expected value, so we're going to get positive delta weights in the dense layer here for all the synapses. But the batch delta weight is still negative, and that's because the last data row, we had the opposite thing going on here, and the difference between the output and expected value for that data row was much bigger, so that's why the net here is negative. This is the iterative mean of all old delta weights and the new one. Let's backpropagate again now. So we place the filter over here, and we're going to get the same positive delta weight values here because the outputs are the same. And then we place the filter over the next location. And since the output here is 0, we're not going to see a change to this delta weight, whereas this one should become bigger. So this one is almost twice as big as this one now.